Out there in the endless dark, the universe holds secrets that have puzzled humanity for generations. We gaze up at the stars and wonder what lies beyond our understanding. And the truth is, despite all our advances, space remains one of the greatest frontiers of the unknown. From the bizarre behavior of distant galaxies to the strange signals echoing across the cosmos, there are phenomena so perplexing that even our brightest minds are left without answers. It's a reminder that for all we think we know, the universe is still full of mysteries waiting to be unraveled. And that sense of wonder is what drives us to keep exploring, keep questioning, and keep searching for meaning in the vast expanse above. Today, we're setting out on a journey to explore 25 of the most baffling space phenomena that scientists still can't explain. These aren't just curiosities, they're cosmic puzzles that challenge the very foundations of physics and astronomy. Imagine forces so powerful they warp the fabric of space-time, or objects so strange they defy every law we thought was unbreakable. This is about more than just mystery. It's about the edges of human knowledge, the places where our understanding ends and the true magic of the cosmos begins. And as we venture into these enigmas, you'll see that the universe is far stranger, far more magnificent than we often give it credit for. So settle in and open your mind to the possibilities, because what you're about to discover will leave you in awe. From dark energy accelerating the expansion of the universe to rogue planets wandering alone through the void, each of these 25 phenomena tells a story of how much we have yet to learn. This is an invitation to wonder, to curiosity, and to the shared human desire to reach beyond what we know. Whether you're a seasoned space enthusiast or someone simply captivated by the night sky, there's something here that will spark that sense of amazement we all felt as children looking up at the stars. Let's begin this exploration together and uncover the mysteries that lie waiting in the great unknown. Our journey into the cosmos's greatest puzzles begins not in the depths of a distant galaxy, but much closer to home with a single, staggering blip that lasted for just 72 seconds. On August 15, 1977, a radio telescope known as the Big Ear at Ohio State University was engaged in its routine sweep of the sky, listening for the faint whispers of the universe. That night, it heard a shout. A volunteer researcher named Jerry Amon was reviewing the computer printouts days later when his eyes landed on a string of data so extraordinary he circled it, and in a moment of pure, stunned reaction, scribbled one word in the margin: "Wow." This wasn't just any signal. It was a powerful, focused burst of radio waves that was almost perfectly tuned to the hydrogen line frequency, precisely the band scientists had theorized an advanced extraterrestrial civilization might use to broadcast its presence. The signal was narrowband, meaning it was concentrated on one specific frequency, a hallmark of an artificial transmitter rather than any known natural cosmic event. It came from the direction of the constellation Sagittarius, and for its brief duration, it was over 30 times stronger than the background noise of deep space. Despite its breathtaking promise, the WOW signal revealed its most frustrating characteristic almost immediately. It was a one-time event. It has never been heard again. In the decades since that summer night, astronomers have pointed countless radio dishes toward that same patch of sky, conducting exhaustive searches for a follow-up, a repeat, anything that could provide a clue. Every attempt has met with silence. This singular nature is what fuels the mystery and pushes scientists to consider every possible explanation, natural or otherwise. Some have proposed it was a signal bouncing off a piece of space debris or a secret military transmission. But these ideas often struggle to account for the signal's unique profile and its origin in interstellar space. One of the most discussed natural explanations emerged in 2016, suggesting the signal might have been caused by the passage of a comet. The theory was that hydrogen clouds surrounding comets could emit radio waves at the right frequency. However, this idea was quickly met with strong skepticism from the astronomical community. Critics pointed out that the specific comets proposed were not actually in the right area of the sky at that exact time, and more fundamentally, such cometary emissions would be far too weak and broad to account for the intense, narrowband signal that was detected. The comet hypothesis, while creative, ultimately fell short, leaving the door open to more profound possibilities. The WOW signal remains a solitary enigma, a fleeting hello from the cosmos that continues to challenge our place in the universe and asks the most compelling question of all. If it wasn't us, then who or what was calling? While the WOW signal represents a fleeting and singular mystery, our next phenomenon is a constant, pervasive presence throughout the cosmos, a ghost that makes its presence known only by the gravitational pull it exerts on everything we can see. This is the enigma of dark matter. Imagine looking at a giant spiral galaxy like our own Milky Way, a breathtaking pinwheel of stars, gas, and dust all spinning around a central core. According to the well-established laws of gravity, stars on the outer edges of that spiral, far from the central mass, should be moving much more slowly than those closer in. Think of our solar system. Pluto, way out on the fringe, orbits the Sun at a snail's pace compared to Mercury, which zips around at a blistering speed. But when astronomers like Vera Rubin began measuring the rotational speeds of stars in distant galaxies in the 1970s, they found something that defied all expectation. The stars on the outskirts were moving just as fast as those near the center. The entire galaxy was rotating as if it were a solid disk, not obeying the gravitational pull of the visible matter alone. The only logical conclusion was that galaxies are embedded within vast, massive halos of something we cannot see, a mysterious substance that provides the extra gravity to hold these fast-moving stars in their orbits. This gravitational evidence doesn't stop at galaxy rotations. Another profound line of proof comes from a phenomenon predicted by Einstein's theory of general relativity, gravitational lensing. The mass of a massive object, like a galaxy cluster, warps the very fabric of space-time around it, bending the path of light coming from more distant objects behind it. By measuring how much this light is distorted, astronomers can essentially weigh the cluster. Time and again, these measurements reveal that the amount of mass required to create the observed bending is far greater than the total mass of all the visible stars, gas, and dust in that cluster. There is simply far more matter there than we can account for, and it refuses to interact with light in any way, making it completely dark. So what do we actually know about this invisible component of the universe? Through decades of observation and deduction, scientists have been able to paint a surprisingly detailed profile of what dark matter must be like, even though we've never directly touched it. We know it has to be cold, meaning its particles move relatively slowly. This is crucial for explaining how galaxies and the large-scale structure of the universe formed. If dark matter were hot and fast-moving, it would have smoothed out these structures, preventing galaxies from clumping together in the way we observe. We also know it is overwhelmingly collisionless. Unlike normal matter, which bumps into itself, slows down, and clumps forming stars and planets, dark matter particles seem to pass right through each other and through normal matter without a trace. This is why dark matter forms these diffuse halos around galaxies instead of collapsing into disks or lighting up in the center. The hunt to identify what dark matter actually is constitutes one of the greatest experimental efforts in modern science. The leading theoretical candidate for decades has been a class of particles known as WIMP, or weakly interacting massive particles. These hypothetical particles would have a mass anywhere from tens to thousands of times that of a proton, and would interact with normal matter only through gravity and the weak nuclear force, the same force responsible for radioactive decay. This incredible faintness explains why they are so difficult to detect. laboratories around the world have been built deep underground, shielded from cosmic rays, in hopes of catching the rare, minuscule bump of a WIMP colliding with an atom in a super-sensitive detector. Yet after decades of searching with increasingly sensitive instruments, not a single confirmed WIMP signal has been found. This lack of detection has fueled the rise of another compelling candidate, the action. Originally proposed to solve a completely different problem in particle physics, actions are theorized to be incredibly light, possibly billions of times lighter than an electron. While they would be far more numerous than WIMP to account for the same total mass, their detection requires an entirely different, equally ingenious approach. Experiments are searching for actions by using powerful magnetic fields to try and convert them into faint microwave photons in a resonant cavity, essentially turning a particle of dark matter into a tiny flash of light we can measure. The frustration for physicists is palpable. We can map the gravitational influence of dark matter with exquisite precision. We know it makes up about 85% of all the matter in the universe, and yet it continues to elude every single one of our attempts to identify its fundamental nature. This invisible scaffolding holds the universe together, and its secret remains one of the most profound and humbling puzzles in all of science. If dark matter is the mysterious, invisible glue holding the cosmos together, then dark energy is its polar opposite, a baffling, repulsive force that is actively and violently tearing the universe apart. For much of the 20th century, astronomers operated under one of two core assumptions. Either the universe was static and unchanging, or it was expanding from its Big Bang birth but gradually slowing down over time due to the relentless pull of gravity. Everything we understood about physics pointed to a cosmos where the collective gravity of all matter would act as a brake on this expansion, perhaps one day even pulling everything back together in a cataclysmic big crunch. That all changed in 1998, when two independent teams of researchers made a discovery so shocking and counterintuitive that it would ultimately win them the Nobel Prize. They were measuring the distances to extremely far-off Type 1, a supernova stellar explosions so consistent in their brightness that they serve as perfect standard candles for gauging vast cosmic distances. By comparing how far away these supernovae were to how much their light had redshifted, a measure of how fast they were moving away from us, the teams could chart the history of the universe's expansion. To their utter astonishment, they found that the most distant supernovae were significantly fainter and therefore farther away than their redshifts indicated they should be. The only possible explanation was that the expansion of the universe wasn't slowing down at all. It was speeding up. Some unknown force was acting against gravity, pushing galaxies apart from one another at an ever-increasing rate. This revelation pointed to a form of energy inherent to the very fabric of empty space itself, a concept that Einstein himself had once proposed and then famously discarded as his greatest blunder. He called it the cosmological constant, a mathematical fudge factor he introduced into his equations of general relativity to force a static, unchanging universe, which was the prevailing belief at the time. When Edwin Hubble later discovered the universe was in fact expanding, Einstein abandoned the idea. But with this new discovery, the cosmological constant was resurrected in a spectacular fashion. This energy of empty space, now dubbed dark energy, behaves as a kind of anti-gravity. Where gravity pulls, dark energy pushes. And because it is a property of space itself, the more the universe expands, the more space there is, and the more powerful this repulsive force becomes. This creates a runaway feedback loop, ensuring the acceleration continues indefinitely, leading to a cold, dark, and lonely fate for the cosmos as galaxies are pushed beyond each other's observable horizons. The simplest explanation for dark energy is this vacuum energy, a consequence of quantum mechanics which suggests that empty space is not truly empty at all. At the tiniest scales, a seething foam of virtual particles constantly pops in and out of existence, and this activity should endow every cubic centimeter of space with a certain amount of energy. This is where we run into one of the most profound problems in all of theoretical physics, known as the vacuum catastrophe. When physicists attempt to calculate how much energy this quantum vacuum should contain, the number they arrive at is absurdly, impossibly large. It exceeds the value we observe for dark energy by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst prediction in the entire history of science. The discrepancy is so vast that it cannot be explained by any known physics. If the quantum vacuum energy were even remotely as powerful as the math suggests, the repulsive force would have been so immense that it would have ripped apart every atom, star, and galaxy before any of them could even form. The universe as we know it would never have existed. This staggering mismatch between theory and observation is the heart of the cosmological constant problem. We have two of the most successful theories in human history, quantum mechanics and general relativity, and they provide two completely different, utterly irreconcilable answers for what the energy of empty space should be. One theory predicts a number that is unimaginably colossal, while the other, through direct observation of the cosmos, measures a value that is extraordinarily tiny but not zero. This isn't just a small rounding error. It is a fundamental crisis that points to a deep flaw in our understanding of reality. Some physicists hope that a future theory of quantum gravity, like string theory, might somehow provide a mechanism that cancels out almost all of this vacuum energy, leaving behind the tiny remnant we see as dark energy. Others propose that dark energy isn't a constant at all, but a dynamic field that has changed over the history of the universe, an idea sometimes called quintessence. But so far, every alternative explanation brings its own set of complications and lacks any definitive evidence. Dark energy remains the ultimate wild card, constituting about 68% of the total energy in the universe and dictating its ultimate fate, all while remaining almost completely mysterious to the physicists struggling to explain its true nature. Leaving behind the enigmatic force of dark energy shaping the universe's fate, we now turn our attention to a cosmic pattern so peculiar it has earned an equally dramatic name, the axis of evil. This phenomenon isn't about some malevolent force, but rather a startling and deeply unexpected alignment found etched into the oldest light we can see, the cosmic microwave background. This afterglow from the Big Bang is the universe's baby picture, a snapshot from when it was just 380,000 years old, and it is remarkably uniform. Tiny fluctuations in its temperature, mere millionths of a degree, reveal the seeds that would eventually grow into the galaxies and clusters we see today. According to a cornerstone of modern cosmology known as the cosmological principle, these fluctuations should be completely random. The universe on its largest scales should have no preferred direction. It should be homogeneous and isotropic, meaning it looks the same in every direction. There should be no up, down, left, or right in the grand cosmic scheme. This principle is the foundation upon which we've built our entire understanding of the cosmos. That's why the discovery of the axis of evil is so profoundly disquieting. When scientists created a full sky map of this ancient light using data from the Wilkinson microwave anisotropy probe, they noticed something that defied all expectation. Some of the largest scale patterns in the temperature fluctuations weren't random at all. They appeared to be aligned or correlated with the plane of our own solar system and the direction of the sun's motion through the galaxy. It's as if the universe's primordial blueprint somehow knew about the location of our tiny, insignificant planet billions of years before it even formed. This is a correlation that simply should not exist. Our solar system is a microscopic speck in a vast cosmos, and its orientation should be completely irrelevant to the large-scale structure of the entire universe. Finding any link between the two is like discovering that the foundation of a skyscraper was poured to perfectly match the pattern of a single piece of gravel that would later be dropped in the parking lot. Scientists have scrambled to find a conventional explanation. The most obvious and hoped-for culprit would be some form of systematic error or contamination in the data. Perhaps the satellite itself was picking up interference from our own galaxy's dust or from the solar system's magnetic field. Maybe the instrument needed a better calibration. Yet after years of intense scrutiny and with even more precise data from the Planck satellite, the anomaly stubbornly persists. Researchers have refined their analyses, subtracted every possible known foreground source of contamination, and the strange alignment remains. It refuses to be explained away as mere noise or an instrumental glitch. This forces cosmologists to consider far more radical possibilities. Could it be that the cosmological principle itself is flawed? Is it possible that the universe is not the same in all directions on its very largest scales, and we just happen to be in a special place? This idea, reminiscent of a pre-Copernican Earth-centered universe, is deeply unsettling to scientists. Alternatively, the alignment might be a hint of something even stranger happening in the primordial universe before the cosmic microwave background was even emitted, a period we have no direct observational window into. The axis of evil stands as a chilling reminder that our most fundamental assumptions about the cosmos are still open for debate. It's a subtle pattern, a ghost in the machine of the universe's oldest data, but its implications are monumental. It challenges the very notion of an isotropic universe and raises the haunting possibility that we are, in some way we do not yet understand, connected to the cosmos's deepest structures in a way that physics says we shouldn't be. It remains one of the most unresolved and philosophically troubling puzzles in all of cosmology. From the grand, unsettling alignment of the cosmos itself, we now journey inward to a mystery that played out much closer to home, a tiny but persistent tug on humanity's first emissaries to the stars. In the early 1970s, NASA launched two pioneering spacecraft, Pioneer 10 and Pioneer 11, on a historic trajectory that would take them past Jupiter and Saturn, and then on a one-way trip out of our solar system. For decades, as these intrepid probes sailed into the dark, navigators at NASA's Jet Propulsion Laboratory meticulously tracked their positions using the subtle Doppler shift in their radio signals. By measuring the precise frequency of the signal coming back to Earth, they could calculate the spacecraft's velocity with astonishing accuracy. Everything was proceeding according to the well-established laws of orbital mechanics, the same math that allows us to send a rover to Mars with pinpoint precision. But then, something strange emerged from the data. Both spacecraft were experiencing a constant sunward deceleration. An incredibly faint but undeniable force, equivalent to just 10 billionths of the gravity we feel on Earth, was ever so gently pressing on the brakes. It was as if they were driving up an invisible hill, and this effect became known as the Pioneer Anomaly. For years, this minuscule drift was a major puzzle in deep space navigation. Was it evidence of some new physics? Could it be a flaw in our understanding of gravity itself? Some theorists proposed exotic explanations, including the influence of unseen dark matter in our solar system, or even modifications to Einstein's theory of general relativity. The idea that our foundational laws might be slightly incorrect at great distances was both thrilling and deeply concerning for physicists. The mystery deepened further when similar, though less pronounced, anomalies were noted in the trajectories of other distant spacecraft, like the Galileo and Ulysses missions. It seemed as though a universal, unknown force was acting on everything we sent into the deep cold of the outer solar system. The painstaking, decades-long investigation to solve this riddle is a masterclass in scientific detective work. A dedicated team led by physicist Slava Turyshev began a monumental effort to recover and analyze decades-old data from the probes. even digging up vintage magnetic tapes and old command logs to reconstruct the entire mission history. They developed incredibly sophisticated models of the spacecraft, accounting for every possible nudge and push. They considered the gentle pressure of the solar wind, the tiny gravitational pull of undiscovered asteroids, and even the minuscule drag from interplanetary dust. One by one, these possibilities were eliminated. Their effects were far too weak to account for the observed anomaly. The breakthrough finally came when the team focused not on external cosmic forces, but on the spacecraft themselves. The Pioneers were powered by radioactive plutonium, and that meant they were also heaters, constantly generating warmth from their internal systems. The team built a detailed thermal model of the probes and realized that this heat was radiating away from the craft unevenly. More heat was being emitted from the back of the spacecraft's main dish antenna, which faced toward the Sun and Earth, than from the front. This created a tiny but constant recoil force, much like the gentle push you feel when warm air rises from a radiator. The photons carrying that heat away were imparting a tiny momentum push back on the spacecraft, in precisely the right direction and of the right magnitude to explain the anomalous deceleration. With this thermal explanation confirmed, the Pioneer anomaly was largely considered solved, a triumph of meticulous analysis over exotic speculation. However, like any good mystery, a faint whisper of intrigue remains. While the thermal radiation account fits the Pioneer data almost perfectly, some researchers point out that other spacecraft, like New Horizons as it journeys toward the Kuiper belt, might be experiencing effects that are not fully explained by their own thermal models. This suggests that while the primary case of the Pioneer anomaly may be closed, the complete book on subtle, non-gravitational forces acting on deep space probes might not yet be fully written. It serves as a powerful reminder that even in the seemingly settled realms of physics, the universe demands our utmost attention to detail, proving that sometimes the biggest mysteries have the smallest, most unexpected origins. But if the universe is so vast and ancient, teeming with billions of planets that could cradle life, a deeply unsettling question naturally arises, one famously captured by the physicist Enrico Fermi during a casual lunch conversation in 1950. Where is everybody? The sheer scale of the cosmos is almost impossible to comprehend. Our Milky Way galaxy alone contains an estimated 100 to 400 billion stars. Many of these stars are billions of years older than our Sun, and we now know that a significant fraction of them host planets orbiting within the habitable zone, that Goldilocks region where temperatures could allow for liquid water, a key ingredient for life as we know it. Even if the probability of intelligent life emerging on any given planet is infinitesimally small, the colossal numbers involved seem to demand that the galaxy should be buzzing with activity. By any reasonable calculation, spacefaring civilizations should have arisen millions, if not billions, of years ago, and their presence should be unmistakable. They could have colonized vast swaths of the galaxy by now, or at the very least, their communications and artifacts should be everywhere. Yet when we train our telescopes on the heavens and listen intently, we are met with a profound and eerie silence. This glaring contradiction between the high probability of extraterrestrial intelligence and the complete absence of any observable evidence is the heart of the Fermi Paradox. Over the decades, scientists and thinkers have proposed a multitude of solutions to this paradox, and they range from the hopeful to the utterly terrifying. One of the most discussed and sobering concepts is the idea of the Great Filter. This theory suggests that there exists some kind of nearly insurmountable barrier that prevents life from progressing to the stage of becoming a visible interstellar civilization. The frightening part is we don't know where this filter lies. It could be behind us, meaning that the evolution of complex, intelligent life is so extraordinarily rare that we have already passed through the bottleneck. Perhaps the jump from single-celled life to multicellular organisms is the miracle, and we are the lone success story in our galactic neighborhood. the more terrifying possibility is that the Great Filter lies ahead of us. This would mean that while life and intelligence might be common, there is some inevitable catastrophe that awaits all technologically advanced species. This could be self-annihilation through nuclear war, a runaway biotechnology disaster, an AI uprising, or perhaps some unforeseen cosmic event that regularly sterilizes planets. If this is the case, then our own future may hold a silent, unavoidable doom that has befallen every other civilization that came before us. On a far more optimistic, though equally mysterious, note is the zoo hypothesis. This idea proposes that advanced extraterrestrial civilizations are indeed out there and are fully aware of our existence, but they have deliberately chosen to conceal themselves from us. The analogy is that our planet is like a protected wildlife preserve or a laboratory, and they are observing our development from a distance without interfering, adhering to a strict policy of non-intervention. This would explain the silence. We are not receiving signals because they are intentionally not sending any our way until we reach a certain level of maturity or technological sophistication. Another variation is the planetarium hypothesis, which suggests that our entire observable universe could be a sophisticated simulation or a projection designed to appear empty, effectively isolating us within a custom-made reality. While these ideas are fascinating, they are ultimately untestable with our current science, placing them in the realm of compelling speculation rather than hard theory. Other explanations are more practical, grounded in the sheer difficulty of interstellar travel and communication. The distances between stars are so unimaginably vast that even a civilization far older than ours might find it impractical to physically travel between them. They might send out probes instead, which could be silently floating through our solar system right now, too small or too advanced for us to detect. There's also the possibility that we are simply listening for the wrong things. We primarily search for radio signals, but a vastly advanced culture might have moved on to a completely different and undetectable technology for communication, like neutrino beams or something we haven't even conceived of yet. We could be surrounded by conversations happening on a channel we don't know how to tune into, or perhaps civilizations are simply too transient. The lifespan of a technological species might be tragically short, burning brightly for only a few centuries before collapsing under the weight of its own success, leaving behind silent ruins on a distant world. The most humbling and for some the most lonely possibility is that we are, in fact, the first. In this scenario, the conditions for intelligent life only recently fell into place in the universe's 13.8 billion-year history, and we are the pioneers, the first species to gaze up at the stars and wonder if we are alone, destined to one day become the ancient aliens that future civilizations will whisper about. The Fermi Paradox holds up a mirror to humanity, forcing us to confront our own future and our place in a cosmos that remains stubbornly, mysteriously quiet. While the Fermi Paradox confronts us with a universe that appears silent, our telescopes have actually begun to pick up screamingly loud, fleeting signals that are anything but a sign of intelligent conversation. These are fast radio bursts, or FRB, and they are among the most energetic and mysterious events ever detected in the cosmos. Imagine a flash of radio waves so powerful that in just a few thousandths of a second, it releases more energy than our sun does over the course of several decades. This isn't a sustained signal from a beacon. It's a cosmic shout, a brilliant blip that appears out of nowhere from a source billions of light years away, and then vanishes almost as quickly as it arrived. The story of their discovery began in 2007, when astronomer Duncan Lorimer and his student were poring through archived data from the Parkes Radio Telescope in Australia, searching for new pulsars. Buried in observations from 6 years prior, they found a single, spectacular burst that was so intense it saturated the telescope's detectors. For a time, the scientific community was skeptical, wondering if this Lorimer burst was some strange terrestrial interference or a one-off glitch. But then other telescopes around the world began finding them too. These events were real, and they were coming from far beyond our galaxy. The mystery only deepened with a pivotal discovery in 2016. While most FRBs were one-off events never to be heard from again, astronomers found one source, now known as FRB 1211-2, that was repeating. This was a monumental clue. It meant the source of these bursts couldn't be a cataclysmic, self-destructing event like a star blowing itself apart. Whatever was creating these repeating bursts had to be incredibly robust, surviving the unimaginable forces required to generate such a flash over and over again. The hunt was on to pinpoint their origins, and the results were as stunning as the bursts themselves. By measuring a phenomenon called plasma dispersion, how the burst's different radio frequencies are slowed down by free electrons in space, astronomers can calculate how much material the signal has traveled through and thus estimate its distance. This is how we know these bursts are truly extragalactic, often originating from galaxies billions of light years away. In a series of scientific triumphs, powerful arrays of telescopes have managed to triangulate the positions of several FRBs, tracing them back to their host galaxies. These aren't just random points in the void. They have been localized to the spiral arms of distant galaxies, regions brimming with star formation. This crucial detail points strongly to their progenitors being connected to the lives and deaths of massive stars. The current leading suspect in the case of these cosmic outbursts is a type of stellar corpse known as a magnetar. A magnetar is a highly magnetized neutron star, the collapsed, ultra-dense core of a giant star that went supernova. To grasp its power, consider that a magnetar's magnetic field is 1,000 trillion times stronger than Earth's. It's a magnetic field so intense that it could wipe a credit card from halfway to the moon and distort the very shape of atoms. The theory suggests that these stars can experience colossal starquakes, where their rigid crusts crack under intense magnetic pressure, releasing titanic flares of energy. Alternatively, a torrent of material falling onto a magnetar from a companion star could trigger an immense explosion, channeling energy into a narrow beam of radio waves that we see as a fleeting flash when it happens to sweep across our line of sight. This model elegantly explains the incredible energy, the millisecond duration, and the repeating nature of some bursts. Supporting this, in April 2020, a magnetar within our own Milky Way galaxy erupted with a radio burst that, while much weaker due to its proximity, shared striking characteristics with the distant cosmological FRBs. It was the smoking gun that proved neutron stars are indeed capable of producing such phenomena. Yet, for all the compelling evidence, the case is not entirely closed. The magnetar theory beautifully explains many FRBs, but the universe, in its infinite creativity, seems to have more than one trick up its sleeve. Some detected bursts have exhibited levels of energy and bizarre patterns that push the limits of what we believe even a magnetar can produce. This has kept the door open for more exotic, though less likely, explanations. Some have proposed collisions between incredibly dense objects, like two neutron stars merging or a neutron star being consumed by a black hole. Others have even revisited the possibility of artificial origins, such as power beams from gigantic light sails on interstellar spacecraft, though most scientists consider this a highly speculative last resort rather than a primary theory. The enduring enigma of fast radio bursts is a perfect example of how a new window into the universe always reveals new and unexpected phenomena. They are not whispers in the dark, but violent, brilliant screams from across the cosmos. And while we are getting closer to understanding the throat they come from, their full story remains one of the most electrifying puzzles in modern astronomy. While the violent crackle of fast radio bursts echoes from across the cosmos, another mystery has been unfolding much closer to home, centered on a single, unassuming star located about 1,500 light-years away in the constellation Cygnus. This is KIC 8462852, but you almost certainly know it by its more popular name, Tabby's star, named after the astronomer who led its investigation, Tabby. The story begins with the Kepler Space Telescope, a revolutionary mission designed to find planets by staring incessantly at a single patch of sky, watching for the telltale periodic dimming that occurs when an exoplanet transits or passes in front of its host star. These dips are usually tiny, predictable, and rhythmic. A Jupiter-sized planet might cause the star's light to drop by about 1%, and it will do so like clockwork every orbit. Tabby's star defied every single one of these expectations. The data from Kepler revealed not gentle, repeating dips, but a series of bizarre, extreme, and utterly chaotic dimming events. At one point, the star's light plummeted by a staggering 22%. To put that in perspective, even a Jupiter-sized object would only block about 1% of the light. To cause a 22% dip, you would need an object or a collection of objects nearly half the width of the star itself. This was completely unprecedented. Furthermore, the dips were irregular and asymmetric. Some lasted for days while others stretched on for weeks. The light curves didn't show the clean, symmetrical U-shape of a planet transit, but instead were jagged and strange, with some dips featuring a steep drop and a slow rise or vice versa. It was as if something truly colossal and oddly shaped was intermittently drifting in front of the star, blocking its light in a way that no natural phenomenon we knew of could easily explain. The initial and most natural explanation proposed was a massive swarm of comets. The idea was that a family of icy bodies, perhaps disturbed by the gravity of a passing star, could have been shattered into a vast cloud of debris. As this cloud orbited Tabby's star, its uneven density and distribution could account for the irregular, deep dimming patterns. While this was a creative and plausible astrophysical solution, it had its problems. To create dips as deep as what was observed, the number of comets required would be almost implausibly vast, numbering in the hundreds of thousands or even millions, all operating in a strangely coordinated swarm. It was a solution that seemed to stretch the limits of credibility. It was this struggle to find a convincing natural answer that opened the door to a far more spectacular, though far less likely, possibility: alien megastructures. Specifically, scientists and the public alike began to speculate about a Dyson sphere, a hypothetical concept proposed by physicist Freeman Dyson. The idea is that a civilization vastly more advanced than our own might eventually harness the entire energy output of its star by constructing a giant swarm of orbiting solar collectors, a megastructure that would partially enclose the star. Such a vast artificial construction would be made of materials that don't exist in nature and would likely have an irregular shape, perfectly accounting for the strange, deep, and aperiodic dimming of Tabby's star. The allure of this theory was undeniable, capturing the world's imagination and propelling this distant star to international fame. This launched one of the most intense and widespread astronomical investigations in recent history. Ground-based observatories and amateur astronomers around the world joined a citizen science campaign to keep a constant watch on the star, hoping to catch it in the act of dimming again. When it did, the key was to measure the dimming at different wavelengths of light. This is a crucial diagnostic tool. A solid object like a planet or an alien megastructure would block all wavelengths of light equally. However, if the material blocking the light were made of fine dust particles like those found in a comet's tail, it would block blue light more effectively than red light. This is the same reason our sun looks red at sunset. Dust in the atmosphere scatters the blue light away. The results from these observations have steadily, and for some, disappointingly, pointed away from solid megastructures and back towards dust. During major dimming events, the dimming was found to be significantly more pronounced in blue light than in red light. This is the definitive signature of dust, not a solid object. Further long-term studies revealed another clue. the star has also been undergoing a very gradual, secular dimming over the course of the past century, as seen in old photographic plates. This too is more easily explained by a large, uneven dust cloud orbiting the star rather than a single giant artifact. So is the case closed. Has the mystery of Tabby's star been solved and the dream of a Dyson sphere dismantled? Not entirely. While dust seems to be the primary culprit for the short-term dips, the fundamental question remains: what is creating all this dust, and why is there so much of it in such a strange configuration? The original comet swarm theory still feels inadequate to many astronomers. The amount of dust required is extraordinary, and its behavior is peculiar. Other theories have emerged, including the aftermath of a catastrophic planetary collision that littered the system with debris, or the presence of a giant planet with enormous, dusty rings that are being torn apart by the star's gravity. The true nature of the object or event that initially generated this immense cloud of dust remains an open and compelling question. Tabby's star endures as a powerful symbol of how modern astronomy works. A strange signal prompts wild and wonderful speculation, which in turn drives a global, collaborative effort to collect more data, slowly chipping away at the mystery until a clearer, though often still complex, picture emerges. It may not be aliens, but it's a profound reminder that our universe is still capable of producing phenomena strange enough to fire our imaginations and challenge our understanding. Moving from the enigmatic dimming of a single star, we now shift our gaze to a force operating on a truly unimaginable scale, a cosmic tug-of-war that involves not just our solar system, but our entire galaxy and every one of its neighbors. This is the mystery of the Great Attractor, a gravitational anomaly of such immense power that it is pulling the Milky Way and thousands of other galaxies towards it at a breathtaking 1,400,000 miles per hour. To visualize this, picture our galactic home, a spiral disk of 200 billion stars 100,000 light-years across, hurtling through the void with an entire cluster of galaxies in tow, all drawn by something we cannot directly see. This motion is on top of the overall expansion of the universe. While most galaxies are receding from us due to this expansion, a huge swath of them in one particular direction are moving faster than that expansion would account for, pulled by this hidden gravitational anchor. The story of its discovery begins with mapping the cosmic microwave background, that same ancient light that revealed the axis of evil. This afterglow provides a fixed reference frame against which we can measure the absolute motion of our galaxy through the universe. When this data was combined with detailed surveys of galaxy motions in the 1970s and 80s, a startling pattern emerged. Our local group of galaxies, including Andromeda and the Milky Way, is not just drifting aimlessly. We are part of a much larger river of motion, a flow encompassing thousands of galaxies all heading towards a single point in the sky, located in the general direction of the constellations Centaurus and Hydra. The sheer number of galaxies caught in this flow implied the source had to be colossal, a concentration of mass so tremendous it was dubbed the Great Attractor. But there was an immediate and frustrating problem for astronomers eager to study it. Its location lies directly behind the plane of our own Milky Way galaxy. This region is known as the zone of avoidance. From our vantage point on Earth, this area of the sky is obscured by thick clouds of gas and dust and a dense fog of countless stars that make up the galactic disk. It's like trying to see a distant mountain range through a perpetual, blinding blizzard. For decades, this zone blocked our view in optical light, making the heart of the Great Attractor one of the most significant blind spots in modern cosmology. We knew something huge was there by its gravitational pull, but we couldn't see what it was. Early observations with radio telescopes, which can penetrate the dust, began to peel back the curtain. They revealed that the suspected core of the Great Attractor is a rich cluster of galaxies known as the Norma cluster, located about 220 million light-years away. This cluster is massive in its own right, containing hundreds of galaxies and a huge amount of hot, X-ray emitting gas. For a time, many thought the mystery was solved. The Great Attractor was simply the Norma cluster. But as our maps of the large-scale structure of the universe improved, a new realization dawned. The gravitational pull of the Norma cluster, while significant, was still not nearly powerful enough to account for the immense velocity of the galactic flow we are part of. It was like discovering a large hill was causing a river to bend slightly, when the river's entire course was actually being carved by a hidden mountain range far beyond it. This is where the plot truly thickened. The Great Attractor isn't the final destination. It appears to be just a waypoint, a signpost on a much longer journey. The colossal river of galaxies, including our own and the Norma cluster itself, is being pulled towards something even larger and more distant, a structure of almost incomprehensible size known as the Shapley supercluster. This is the largest known concentration of matter in our observable universe, a gravitational titan containing dozens of massive galaxy clusters and lying over 650 million light-years away. The Great Attractor, then, seems to be the foreground mass, the local downdraft, in a vast cosmic watershed that ultimately drains towards Shapley's immense gravity well. Yet, even this may not be the full story. The measured motion towards Shapley is so great that some cosmologists speculate there could be structures even deeper in the zone of avoidance, beyond the Great Attractor and between us and Shapley, that are contributing to this pull. We are essentially mapping an ocean current by feeling its tug, all while a thick fog hides the whirlpools and trenches creating it. The enduring mystery of the Great Attractor is a humbling lesson in our place in the cosmos. We are not the still center of the universe, but passengers on a galactic arc caught in a current flowing towards an unseen horizon, reminding us that the largest forces shaping our cosmic destiny may still be hidden from our view, waiting for the right technology to reveal their secrets. Just when we thought we had seen it all, the universe delivered a visitor that challenged every assumption we had about the building blocks of solar systems. In October 2017, the Pan-STARRS telescope in Hawaii detected a faint point of light moving at breathtaking speed. Its trajectory was immediately and stunningly clear. This object was not from here. It was not bound by the sun's gravity. It was a traveler from interstellar space, the first such object ever observed passing through our solar system. It was given the name Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. And what a strange messenger it proved to be. From the very beginning, Oumuamua defied easy classification. As telescopes around the world swiveled to track its hurried departure, they struggled to pin down its basic characteristics. The most shocking revelation came from its extreme changes in brightness. As it tumbled through space, its observed brightness varied by a factor of 10, flashing brilliantly and then fading dramatically over a period of hours. This could mean only one thing: its shape was profoundly elongated. To produce such a drastic change in reflected light, scientists concluded Oumuamua had to be shaped like a cigar or a pancake, with a length-to-width ratio of perhaps 10:1. This was unlike any asteroid or comet ever seen in our own solar system, where objects are far more rounded. It was as if we were looking at a cosmic toothpick or a frisbee tumbling end over end. Then came the real head-scratcher. As astronomers precisely plotted its path against the background stars, they noticed something was subtly wrong. Its trajectory could not be explained by gravity alone. Once it had slingshotted around the sun, Oumuamua was accelerating away ever so slightly faster than it should have been. This is a common behavior for comets. As they are heated by the sun, ices on their surface turn to gas and jet out, acting like a tiny thruster that provides a non-gravitational kick. The logical assumption was that Oumuamua was just a weirdly shaped interstellar comet. But there was a massive problem with that theory. Despite intense scrutiny from the world's most powerful telescopes, Oumuamua displayed absolutely no signs of this outgassing. There was no detectable coma, the fuzzy envelope of gas and dust that surrounds a comet's nucleus. There was no tail of debris streaming behind it. It was completely inert, looking for all the world like a bare, silent rock, yet it was accelerating as if it had a silent engine. The scientific community scrambled for explanations that could resolve this paradox. One leading theory proposed that it could indeed be a comet, but one made of very different ices than we're used to. Perhaps it was composed largely of solid nitrogen, like a chunk of a Pluto-like planet that had been chipped off in some distant cataclysm. As the sun warmed its surface, the nitrogen would sublimate directly from a solid to a gas, creating a pure, invisible jet that would provide the thrust without producing any dusty debris that would be visible as a coma or tail. Another idea suggested it could be a hydrogen iceberg, a lump of frozen hydrogen that would similarly sublimate and remain invisible to our instruments. While creative, these theories faced their own hurdles. A nitrogen iceberg would have had to survive a long journey through interstellar space without being eroded by cosmic radiation, and a hydrogen iceberg would likely evaporate long before reaching our inner solar system. The inability of conventional astronomy to easily explain Oumuamua's unique properties led some scientists, most notably Harvard astronomer Avi Loeb, to propose a more extraordinary possibility: that Oumuamua was not a natural object at all, but a piece of advanced technology from an extraterrestrial civilization. The specific idea was that it could be a light sail, a very thin, reflective sheet designed to be pushed by the radiation pressure from starlight. This, proponents argued, would perfectly explain its unusual flattened shape and its non-gravitational acceleration without the need for any visible outgassing. The acceleration was consistent with the gentle, constant push it would receive from sunlight. While this theory captured the public's imagination, the vast majority of the scientific community maintains that an extraordinary claim requires extraordinary evidence and that we must exhaust all natural explanations first. The truth is that Oumuamua's brief visit left us with far more questions than answers. It was a one-of-a-kind data point, a fleeting glimpse of the kind of material that travels between stars. By the time we realized how peculiar it was already too far away and too faint to observe further. It has now vanished into the depths of space, leaving behind a legacy of mystery and a powerful reminder that the universe is capable of crafting objects far stranger than anything we have yet dreamed up in our own celestial backyard. But the moon, our seemingly inert and familiar companion, holds a secret locked in ancient rock that challenges our very understanding of how planetary magnetic fields are born. When Apollo astronauts brought back samples from the lunar surface, they carried with them pieces of a puzzle that would take decades to solve. These rocks, some over 3 billion years old, contained a stunning record: they had been magnetized. This was clear evidence that the moon once possessed a magnetic field, a protective shield generated by a churning, liquid metal core, much like the one that protects Earth today. The sheer existence of this ancient lunar dynamo is a profound enigma. According to all our conventional models, a magnetic field requires a molten, convecting core and a sufficiently rapid spin to act as a cosmic generator. The moon is and always has been a small body. It should have cooled and solidified its core relatively quickly after its violent formation. Its spin is also glacially slow, taking nearly a month to complete a single rotation. By every standard rule of planetary physics, the moon should never have been able to generate or sustain a global magnetic field, especially not one that, at its peak over 3 billion years ago, might have been even stronger than Earth's is right now. The leading theory to explain this impossibility involves revisiting the moon's dramatic origin story. The most widely accepted model, the giant impact hypothesis, suggests the moon was born from the debris of a cataclysmic collision between a young Earth and a Mars-sized object named Theia. This theory elegantly explains the Moon's composition and its orbit, but it might also hold the key to its magnetic mystery. The incredible energy of that impact, along with the subsequent process of accretion, would have left the early Moon scorching hot, likely with a fully molten outer core. Furthermore, in its infancy, the Moon was much closer to Earth, and the immense gravitational tug of war would have created powerful tidal forces, flexing and kneading the lunar interior. This tidal heating could have acted like a built-in furnace, keeping the core molten and stirring it vigorously for billions of years longer than its small size would normally allow. This combination of primordial heat and continuous tidal energy might have been just enough to power a dynamo capable of generating that surprisingly strong magnetic field. However, even this compelling story has its complications. While tidal heating is a powerful engine, the Moon's orbit has been gradually expanding away from Earth over billions of years. As the distance increased, the strength of these tidal forces would have diminished. Computer models suggest this source of energy might have faded away before the Moon's magnetic field itself eventually died out, which is thought to have happened around 1 billion years ago. This has prompted scientists to investigate other potential power sources for the lunar dynamo. One fascinating possibility involves the crystallization of the Moon's core. As the molten iron in the core slowly cooled and began to solidify, the lighter elements within it, like sulfur, would have been pushed out and upward. This process, akin to the convection in a gently simmering pot, could have provided the necessary movement to sustain a magnetic field for a long period, even after the primary sources of heat had begun to wane. It's a delicate balancing act of chemistry and physics happening deep within a small, rocky world. The mystery of the Moon's magnetic field is more than just a curious academic footnote. It forces us to reconsider the inner lives of all small planetary bodies. If the Moon, with its slow spin and modest size, could manage such a feat, then perhaps other moons and dwarf planets in our solar system and beyond could have harbored similar protective shields in their pasts, which might have had profound implications for their potential to host atmospheres or even life. The silent, grey face of the Moon we see today belies a fiery, dynamic, and magnetically active youth, a history written in the invisible alignment of minerals within its oldest rocks. Unraveling this puzzle requires peering back in time through geology and physics, a constant reminder that even our closest celestial neighbor still has fundamental secrets to reveal about how planets work. Yet for all the strange visitors and magnetic mysteries within our own system, some of the most perfectly geometric wonders are found orbiting far beyond Earth, gracing the skies of a gas giant. High above the cloud tops of Saturn's North Pole, a storm rages that defies all earthly notions of weather. It is a hurricane of staggering proportions, but its most breathtaking feature is not its power but its shape. For over 4 decades, since it was first glimpsed by the Voyager probes in the 1980s and later studied in exquisite detail by the Cassini mission, this colossal storm has maintained a form so precise it seems almost artificial, a perfect 6-sided hexagon. Each side is longer than the diameter of Earth, making this an atmospheric feature on a scale that is almost impossible to comprehend. A polygon etched into the clouds of a planet that should only know how to form ovals and spirals. What makes the hexagon so mesmerizing is its unwavering persistence. Whether patterns on Earth, even the most powerful high-pressure systems, are transient, forming and dissolving over days or weeks. Jupiter's Great Red Spot, while ancient, is a dynamic oval that constantly changes size and shape. But Saturn's hexagon is a monument to stability, a permanent fixture in the planet's northern hemisphere that has endured for decades, and likely much longer, locked in place by atmospheric forces we are still striving to understand. The hexagon itself is not a solid structure but a 6-sided jet stream, a wall of air howling along its perimeter at speeds exceeding 300 miles per hour. Inside this geometric boundary, the weather is surprisingly calm, while the hexagon acts as a barrier, trapping a massive, churning vortex at the very pole, much like a cosmic racetrack confining the storm within its lanes. To unravel this puzzle, scientists have turned not only to telescopes and space probes, but also to laboratory experiments here on Earth. The key lies in the branch of physics known as fluid dynamics, which governs how liquids and gases behave when they flow. Researchers have created simplified models of Saturn's atmosphere using large rotating tanks of water. By placing a small ring at the center of the tank to spin and simulate a jet stream, and then rotating the entire tank to mimic Saturn's spin, they have been able to produce a remarkable result. Polygonal shapes, including hexagons, squares, and octagons, naturally emerge in the fluid. The specific shape that forms depends on the difference in speed between the central current and the surrounding fluid. Essentially, when a fluid layer rotates at a different velocity than the fluid surrounding it, the shear between these two layers can become unstable and break into discrete waves, which then manifest as the straight sides of a polygon. This laboratory success is a crucial piece of the puzzle, demonstrating that such geometric patterns are a natural, if rare, consequence of rotating fluids. It suggests that deep beneath Saturn's visible cloud tops, there is likely a dramatic difference in wind speeds between two atmospheric layers, creating the shear necessary to form and sustain the hexagon. However, while these experiments replicate the shape, they fall short of explaining the Saturnian phenomenon in its entirety. The scale and shear stability of Saturn's hexagon are orders of magnitude beyond anything we can create in a lab. Our tanks are measured in feet, while Saturn's weather systems span thousands of miles. The hexagon has withstood countless interactions with other storms and atmospheric disturbances without ever losing its precise six-sided form, a level of resilience that our current physical models still struggle to account for completely. Several intriguing theories attempt to bridge this gap between the lab and the giant planet. One compelling idea is that the hexagon might be a towering structure that extends hundreds of miles deep into Saturn's atmosphere, its roots anchored in the planet's internal weather patterns. This great depth would give it immense inertia, allowing it to resist forces that would tear a shallower feature apart. Another possibility involves the unique internal heat of gas giants. Unlike Earth, which is primarily heated by the sun, Saturn generates a significant amount of its own heat from within, left over from its formation. This internal energy might drive convection currents that help reinforce and stabilize the hexagonal pattern, acting like a constant power source for this atmospheric engine. The hexagon stands as a breathtaking example of how the simple, universal laws of physics can combine on an alien world to create something of sublime complexity and beauty, a natural wonder that continues to challenge our understanding of planetary atmospheres. But high above Saturn's geometric perfection, far beyond the protective bubble of our sun's magnetic field, the Earth is constantly being bombarded by invisible bullets fired from the depths of the cosmos. These are cosmic rays, subatomic particles, mostly protons, that race through space at nearly the speed of light. Most of these particles have energies that, while impressive, can be explained by common cosmic events like supernova explosions. However, a tiny fraction of these particles are in a category all their own, carrying so much energy that their very existence seems to defy the laws of physics. We call them ultra-high-energy cosmic rays, and they are the most energetic particles ever observed in nature. To grasp their power, consider that the Large Hadron Collider, our most powerful particle accelerator, can hurl protons with an energy equivalent to that of a well-thrown baseball. An ultra-high-energy cosmic ray, by comparison, packs the punch of a professionally thrown fastball, all concentrated into a single, minuscule subatomic particle. The sheer force involved is staggering, billions of times more powerful than anything we can create on Earth, and their origin is one of the most enduring puzzles in astrophysics. The central mystery isn't just their incredible energy, but the immense journey they must have survived to reach us. Space is not empty. It is filled with the sparse but pervasive cosmic microwave background radiation, the cooled remnant of the Big Bang that permeates every cubic inch of the universe. For a proton traveling across millions of light years, this background radiation is like running a perpetual, universe-sized gauntlet. When an ultra-high-energy proton collides with a photon from this background, it should lose a significant amount of its energy through a process known as the Greisen-Zatsepin-Kuzmin, or GZK cutoff. This fundamental limit, predicted in the 1960s, means that any proton with energy above a certain threshold should be slowed down to below that threshold within a distance of about 150 million light-years. It's a cosmic speed limit. Therefore, the ultra-high-energy cosmic rays that smash into our atmosphere must come from somewhere within our local supercluster of galaxies. They simply cannot have traveled from the distant, ancient universe. This creates a fascinating paradox. We are detecting particles so powerful that only the most extreme events in the cosmos could have created them. But those events must be relatively close to us, astronomically speaking. Yet, when we look around our galactic neighborhood, we see nothing violent or powerful enough to serve as such an accelerator. So what cosmic engines could possibly be capable of this feat? Scientists have proposed several candidates, each more extreme than the last. The primary suspect for decades has been active galactic nuclei, the incredibly luminous cores of galaxies powered by supermassive black holes that are actively feeding on surrounding matter. As material spirals into the black hole at nearly light speed, it creates unimaginable turbulence and magnetic fields that could potentially funnel particles and accelerate them to these unbelievable energies. Another compelling candidate is the shock waves from galaxy clusters colliding with each other, events that release more energy than anything else in the universe since the Big Bang. The chaotic merging of galaxies and the heating of gas to hundreds of millions of degrees within these clusters could provide the perfect environment for particle acceleration on a colossal scale. More exotic theories point to the decay of hypothetical super-heavy dark matter particles from the early universe, or even cataclysmic events like gamma-ray bursts, the most energetic explosions known. The hunt to pinpoint these accelerators is the driving force behind observatories like the Pierre Auger Observatory in Argentina, a sprawling detector array that covers an area of over 1,000 square miles. It doesn't detect the cosmic rays directly, but rather the enormous showers of secondary particles they create when they slam into the upper atmosphere. By studying the direction from which these particles arrived and the nature of their cascading showers, physicists hope to trace their paths back to a source. The results so far have been tantalizing but inconclusive. There have been hints of correlations with nearby active galaxies and other energetic objects, but no smoking gun has been identified. The particles are so rare, arriving at a rate of about 1 per square kilometer per century, that collecting enough data is a painstakingly slow process. Furthermore, because cosmic rays are charged particles, their paths are bent and twisted by the magnetic fields that fill interstellar and intergalactic space, making it incredibly difficult to trace a straight line back to their point of origin. It's like trying to find the source of a river by following a single drop of water that has been blown about by a chaotic wind. The mystery of ultra-high-energy cosmic rays is a humbling reminder that some of the most violent and powerful engines in the nearby universe are still operating in plain sight, yet remain completely invisible to our conventional telescopes, known to us only by the microscopic shrapnel they fire across the void. While our solar system presents its own geometric wonders, the universe at large is capable of crafting structures of such symmetrical perfection that they seem to defy the chaotic nature of stellar death itself. One of the most stunning examples lies about 2,300 light-years away in the constellation Monoceros, a celestial object so unique it was named simply for its appearance on early photographic plates, the Red Rectangle Nebula. This isn't a vast, billowing cloud like the pillars of creation. Instead, it presents itself as a near-perfect geometric form, an X shape with astonishingly straight sides and a series of horizontal rungs that look like a cosmic ladder. It is a bipolar nebula, meaning it has two opposing lobes of material, but unlike any other known to science, its symmetry is so precise, so unnervingly artificial in its appearance, that it stands as a profound challenge to our standard models of how stars end their lives. The story of the Red Rectangle begins with a central binary star system, a pair of aging suns locked in a tight orbital dance. One of these stars has exhausted the hydrogen fuel in its core and has swollen into a red giant, casting off its outer layers in a steady stellar wind. This is a common prelude to the formation of a planetary nebula, where the ejected gas is illuminated by the intense ultraviolet radiation from the star's hot core, creating a glowing cloud of intricate and often beautiful shapes. But in the case of the Red Rectangle, the presence of the second star is the crucial factor that twists this common process into something extraordinary. The gravitational influence of this companion star is believed to funnel the expelled material into two opposing cones or jets, rather than allowing it to expand in a spherical shell. This is the basic mechanism that creates the bipolar structure, the two lobes that give the nebula its rectangular outline when viewed from the side. However, this binary interaction alone cannot account for the nebula's most baffling features: the razor-sharp straight lines and the series of perfectly spaced equidistant rungs. If the outflow were simply a smooth, continuous wind of gas, we would expect to see softly curving lobes, not a structure with hard edges and distinct rungs. This is where the mystery deepens considerably. The prevailing theory suggests that the central star isn't expelling material in a steady stream, but in fits and starts. It is thought to be pulsing, ejecting matter in periodic outbursts rather than a constant flow. As each new shell of gas expands outward, it rams into the slower-moving material ejected in previous outbursts. This creates a series of shock waves, dense, compressed walls of gas and dust that we see as the nebula's distinctive rungs, much like ripples frozen in time. But the question of the perfectly straight lines remains perhaps the most puzzling aspect. How does a chaotic, turbulent process like a dying star's death throes produce something with the precision of a drafting table? The leading explanation points to a dense, dusty disk that is thought to encircle both stars in the binary system. This torus of material, a byproduct of the stellar interaction, acts as a nozzle. It tightly collimates or focuses the outflowing material into two extremely narrow jets. This is akin to placing your thumb over the end of a garden hose to create a tight, directed stream instead of a diffuse spray. The incredible straightness of the nebula's sides suggests this collimation process is remarkably efficient and stable over long periods. The combination of the pulsed outbursts creating the rungs and the dense disk focusing the flows into straight jets might be the recipe for this cosmic masterpiece. Yet, even this sophisticated model doesn't fully solve the puzzle. The Red Rectangle's symmetry is almost too perfect. The mechanism requires a delicate and prolonged balance of forces. The rate of mass loss, the pulse period, the stability of the circumbinary disk, that seems incredibly fine-tuned. Furthermore, the nebula's striking red color, which comes from unusual carbon-based molecules known as polycyclic aromatic hydrocarbons, adds another layer of chemical complexity to its formation. While the binary star and pulsed outflow theory is our best framework, the Red Rectangle ultimately serves as a brilliant reminder that nature's processes can achieve forms of order and geometry that rival our most precise engineering, revealing that even in death, a star can create a legacy of breathtaking and mysterious beauty. Just when we thought we had a handle on the rules governing the cosmos, the universe delivered another curveball, one that threatens to unravel a foundational pillar of modern astronomy. For decades, the story of galaxy formation has been a story written by dark matter. The theory is elegant and well supported. After the Big Bang, dark matter, with its gravitational pull, collapsed first into vast halos. These invisible scaffolds then drew in normal gas and dust, which cooled, condensed, and eventually ignited into the stars that make up the bright galaxies we see today. In this model, a galaxy cannot exist without its dark matter skeleton. It is the primary ingredient, the cosmic glue that holds everything together. This is why the discovery of galaxy NGC 1052 DF2 was so profoundly shocking. Here was a seemingly mature galaxy that appeared to be missing its skeleton entirely. Discovered by the Dragonfly Telephoto Array, a telescope specifically designed to spot incredibly faint, diffuse objects, NGC 1052 DF2 is an ultra-diffuse galaxy. It's about the size of our Milky Way but contains only about 1/200th of the stars, making it a ghostly, see-through collection of stars. When a team led by astronomer Pieter van Dokkum began studying it, they expected to find the same thing they found in every other galaxy, the overwhelming gravitational signature of dark matter. They measured the velocities of 10 bright star clusters orbiting within the galaxy. The speed of these orbiting clusters is a direct window into the galaxy's total mass. The faster they move, the more mass, both visible and dark, must be present to hold them in orbit. To their astonishment, the clusters were moving surprisingly slowly. The calculated total mass of the galaxy was almost exactly equal to the mass of its visible stars and gas. There was simply no room left for dark matter. This was like weighing a bucket of water and finding it has the exact weight of the empty bucket. The water, the primary component, was seemingly missing. The immediate reaction from the astronomical community was one of intense skepticism, and the debate quickly focused on one crucial variable: distance. The entire calculation hinges on knowing exactly how far away the galaxy is. If NGC 1052 DF2 is closer to us than originally believed, then the galaxy itself would be physically smaller and contain less mass. Its star clusters would also be moving slower for their size, not because of a lack of dark matter, but simply due to the revised scale of the system. This became the central point of contention. Van Dokkum's team used several methods, including the apparent brightness of the star clusters, to place the galaxy about 65 million light-years away. However, a separate analysis using the Hubble Space Telescope's measurements of the brightness of red giant stars' reliable cosmic distance markers suggested a much closer distance of only 42 million light-years. At this closer range, the galaxy's peculiar properties might simply vanish, explained away as a miscalibration. The controversy highlights the incredible difficulty of measuring the vast scales of the universe. A difference of 23 million light-years might seem trivial on a cosmic scale, but for a single galaxy, it changes everything. Proponents of the dark matter-less galaxy have stood by their original distance measurements, and the discovery of a second, similar galaxy, NGC 1052 DF4, which also appears to be devoid of dark matter, has bolstered their case. It seems less likely that two separate galaxies would have their distances so severely misjudged. If these galaxies are indeed missing their dark matter, it forces a monumental rethink. How did such a galaxy form? One fascinating possibility is that it is a failed galaxy. Perhaps it was born from gas that was stripped away from two larger galaxies during a past interaction, a tidal debris field that never had its own dark matter halo to begin with. Another, more dramatic theory speculates that a close encounter with a massive galaxy could have ripped away both its stars and its dark matter, leaving behind the pale, ghostly remnant we see today. The existence of even a single galaxy without dark matter is a double-edged sword for cosmology. On one hand, it seems to break the established model. On the other, it provides a unique and powerful test. If dark matter is a real, physical substance that can be separated from normal matter, as these galaxies suggest, then it severely undermines alternative theories that seek to explain away the need for dark matter by modifying the laws of gravity, like modified Newtonian dynamics or MN. These theories propose that gravity behaves differently at low accelerations, which would explain the rotation curves of galaxies without invoking invisible matter. However, Mund would predict that every galaxy should show the same kinematic anomalies. The discovery of a galaxy that perfectly obeys standard Newtonian gravity, with no dark matter and no Mund-like effects, is a huge problem for such alternatives. In a strange way, a galaxy without dark matter might be the strongest evidence yet that dark matter is real, a tangible thing that can be present or absent, rather than a mere flaw in our understanding of physics. This cosmic paradox reminds us that for every rule we write about the universe, there seems to be an exception waiting in the shadows, challenging us to look deeper and think harder. While the search for phantom galaxies without dark matter pushes the boundaries of cosmology, another hunt is underway much closer to home, on the rusty surface of our planetary neighbor, where a faint whiff of gas has sparked one of the most compelling mysteries in our solar system. The story of Martian methane is a detective story with the highest possible stakes, a puzzle where the clues are measured in parts per billion, and the primary suspect could be nothing less than life itself. On Earth, the vast majority of methane in our atmosphere is produced by biological processes, from the digestive systems of cows to the decomposition of plant matter in wetlands. Of course, it can also be created by geological activity like serpentinization, a reaction between water, carbon dioxide, and certain rocks that occurs deep underground. So when our robotic emissaries on Mars started detecting this gas, it immediately posed a profound question. Are we seeing the faint chemical signature of geological processes on a still active world, or could it possibly be a sign, a whisper of biology? The plot began to thicken with the arrival of the Curiosity rover in Gale Crater. Equipped with a sophisticated onboard chemistry lab called SAM, the rover has repeatedly sniffed out sudden, sharp spikes of methane in the local atmosphere. These aren't constant background levels, they are transient plumes that appear, sometimes elevating methane levels by a factor of 10, and then vanish again within a matter of hours. This transient nature is itself a major clue. Methane shouldn't last long in the Martian atmosphere. Scientists estimate it should be broken apart by ultraviolet radiation from the sun within a few hundred years. The fact that we see these sudden spikes suggests the gas is being released right now from a local, ongoing source. It's not a remnant from the ancient past. It's a modern-day occurrence, as if somewhere near the rover, a tap is being turned on and off. The mystery deepened when data from orbiting spacecraft like the European Space Agency's Trace gas orbiter entered the picture. This satellite, specifically designed to conduct a planet-wide survey of trace gases like methane with incredible sensitivity, has largely reported a baffling contradiction. It has not detected any significant methane in the atmosphere at all from its orbital vantage point. This created a seemingly impossible situation. How could the rover on the ground be standing in a localized cloud of gas that the orbiter flying overhead cannot see? One compelling resolution to this paradox involves timing and destruction. The leading theory suggests that methane is indeed being released from the surface, perhaps primarily at night when the Curiosity rover's ground-level measurements are most consistent. But by the time the sun rises and its ultraviolet light begins to bombard the planet, the gas could be destroyed incredibly quickly in the lower atmosphere before it has a chance to rise and mix into the broader air column where the orbiter is looking. The orbiter might be searching for a signal that has already vanished by morning, while the rover, acting as a local weather station, catches the brief overnight whiff. The frantic search for a geological explanation has produced several strong candidates, all of which point to a far more dynamic and active Mars than we once imagined. The prime suspect is a process called serpentinization, where water, which we know exists as ice and likely as liquid brine underground, interacts with the mineral olivine, which is common in Martian rocks. This reaction produces methane as a byproduct. If pockets of liquid water are still interacting with rock deep beneath the surface, they could be periodically venting this gas through cracks and fissures in the ground, accounting for the transient plumes. Other possibilities include the slow breakdown of ancient organic material delivered by comets and meteorites by the sun's UV light, or even the release of methane stored in ice like compounds called clathrates that could trap the gas underground and release it when the ground is warmed or disturbed. Yet the biological possibility remains, a tantalizing ghost at the feast of data. Methanogens, simple microbial life forms that don't require oxygen, are common in extreme environments on Earth, like deep underground or in hydrothermal vents. They produce methane as a waste product. It is not at all far-fetched to imagine that similar microbes could have arisen on a warmer, wetter Mars billions of years ago and retreated underground as the planet cooled and lost its atmosphere, surviving in isolated aquifers to this day, occasionally venting their metabolic byproducts into the air. The frustrating and exhilarating truth is that our current instruments cannot distinguish between methane made by geology and methane made by biology. The molecule itself is identical. Solving the Mars methane mystery will require more than just detecting the gas. We will need to analyze its carbon isotopes. Life on Earth prefers to use the lighter carbon-12 isotope over the heavier carbon-13. If future rovers or sample return missions could find that the Martian methane is also enriched in carbon-12, it would be the strongest indirect evidence imaginable that we are not alone. Until then, every little spike on a graph is a siren's call, pulling us closer to answering one of humanity's oldest questions. Yet as we grapple with the mysteries right next door, we must also confront the vast, haunting emptiness that exists on the very largest scales of the cosmos, a void so immense and empty it has earned the dramatic nickname, the Great Nothing. This is the Boötes Void, and to call it a cosmic desert would be a profound understatement. Imagine a sphere of space so colossal that it stretches over 330 million light-years across. If you were to place our entire Milky Way galaxy at one edge of this sphere, the opposite edge would be so far away that the light from our galaxy would take over 300 million years to reach it. Within this incomprehensible volume, you would expect to find tens of thousands of galaxies based on the average density of the observable universe. Instead, astronomers have only been able to confirm the existence of a few dozen. It is a staggering underdensity, a near-perfect vacuum on a scale that defies belief, a gaping hole in the cosmic tapestry that seems to swallow entire superclusters of galaxies without a trace. The discovery of this void in the 1980s was a complete accident. Astronomers Robert Kirshner and his colleagues were conducting a redshift survey, meticulously mapping the distances to galaxies in the constellation of Boötes, the herdsman, to better understand the large-scale structure of the universe. What they found was not a web of galaxies, but a profound and unsettling absence. Their initial observations revealed a region hundreds of millions of light-years wide that was almost completely blank. Subsequent, more sensitive surveys have managed to find a handful of galaxies scattered throughout this emptiness, like a few lonely islands in an ocean of nothingness, but the overall picture remains one of extreme desolation. The mere existence of such a void challenges our standard model of cosmology, which is built upon the idea that matter, both visible and dark, is distributed in a largely homogeneous way when viewed at the largest scales. The Boötes Void is a dramatic and glaring exception to that rule. So how does such a monumental nothingness come to be? Cosmologists have developed two primary explanations, one that works within our current understanding and one that is far more radical. The leading and more conventional theory is that the Boötes Void is not a single primordial emptiness, but rather the result of a cosmic coincidence, the merging of several smaller voids. In the widely accepted cosmic web model of the universe, galaxies are not scattered randomly. Instead, they are strung along immense filaments of dark matter, forming a vast, interconnected web. The spaces between these filaments are the cosmic voids. Most voids are relatively small, on the order of 50 to 100 million light-years across. The theory suggests that over billions of years, the gravitational dynamics of the expanding universe can cause these smaller voids to flow into one another and merge, just like soap bubbles coalescing. The Boötes void in this scenario would be a supervoid, the eventual product of many smaller voids merging together over cosmic time. This is a plausible, if rare, outcome of the gravitational mechanics that shape our universe. However, the sheer scale of the Boötes void pushes this idea to its absolute limit. Some researchers argue that even with void merging, it is extraordinarily difficult to create a region of such profound emptiness and immense size under the standard cosmological model. The gravitational pull from the surrounding dense walls of the cosmic web should have drawn more matter into the void over time, preventing it from becoming so drastically underdense. This has led to a more speculative but fascinating alternative, that the void might be evidence of an encounter with a parallel universe. This idea stems from some interpretations of cosmic inflation, the theory that the universe expanded exponentially in the first fraction of a second after the Big Bang. In certain multiverse theories, the bubble of space-time that became our universe might have collided with another bubble universe in the multiverse foam during this inflationary period. Such a collision could have left a kind of scar on our cosmos, a region where the energy density was fundamentally different, resulting in a vast, empty imprint. While this is a highly speculative and currently untestable hypothesis, it illustrates just how deeply puzzling the great nothing truly is. The Boötes void forces us to question the very principles we use to understand the cosmos. Is it a rare but natural occurrence, a statistical fluke that arises from the chaotic process of structure formation? Or is it a sign that our models of the large-scale universe are incomplete, that there are forces or initial conditions we have not yet accounted for? Its enduring mystery serves as a humbling counterpoint to the dense clusters and brilliant galaxies we normally focus on. It reminds us that the universe is defined not only by the glittering nodes of its web, but also by the silent, empty spaces in between, and that within those immense nothingnesses, some of the most profound cosmic secrets might be hiding. But if the vast emptiness of the Boötes void represents a mystery of absence, our next phenomenon presents a puzzle of fleeting presence, one that exists for less than a billionth of a second, yet threatens to overturn a century of scientific understanding. This is the tantalizing and controversial search for the tetraneutron, a potential particle that, by all rights, should not exist at all. To understand why this is so revolutionary, we have to go back to the very basics of what holds the universe together. At the heart of every atom except hydrogen is a nucleus, a tight cluster of protons and neutrons bound by the strong nuclear force, the most powerful force in nature. Protons, with their positive charge, naturally repel each other. It is the neutrons, the neutral particles, that act as the essential nuclear glue, stabilizing the nucleus and allowing it to exist. For decades, the fundamental rule has been that you cannot have a nucleus made only of this glue. According to the standard model of particle physics, systems made solely of neutrons are not stable. A single neutron on its own will decay into a proton, an electron, and an antineutrino in about 15 minutes. A pair of neutrons, a dynatron, cannot form a bound state. They simply fly apart. Even a trineutron, a system of three, is unstable. The forces simply don't work out to bind them together. So the idea of a stable, bound particle made of 4 neutrons, a tetraneutron, is nothing short of heretical. It defies the fundamental theories that have been the bedrock of nuclear physics for generations. The story of this potential discovery is a masterclass in scientific caution and the painstaking process of validating an extraordinary claim. The first significant hint emerged in 2001 from a team of researchers in France working at the Ganel accelerator. They weren't looking for a tetraneutron, they were conducting a different experiment, firing helium isotopes at a target. But in their results, they noticed a peculiar signal. The data suggested that 4 neutrons had been ejected from the reaction and had briefly stuck together, existing as a single, coherent particle for a barely imaginable sliver of time, about 10 to the power of negative 22 seconds. For context, that's a millionth of a billionth of a billionth of a second. The physics community met this announcement with intense skepticism, as it should. The signal was weak, and the interpretation was fraught with potential alternative explanations. Many argued that it could simply be a statistical fluke or the result of 4 independent neutrons appearing to be correlated by chance rather than a true bound state. For over a decade, the 2001 result remained an intriguing but unproven anomaly, a ghost in the data that most physicists filed away as a likely experimental error. The plot thickened dramatically in 2016 when a team at the Riken Research Institute in Japan designed a far more precise experiment to specifically hunt for the tetraneutron. Their approach was different and more direct. They fired a beam of helium-8, a highly unstable and rare isotope, at a liquid helium target. When these nuclei collided, the result was a helium-4 nucleus and, according to their meticulously measured energy signatures, a tetraneutron. The energy missing from the initial reaction products indicated that the 4 neutrons were indeed in a bound, or at least a resonant state. A resonant state is like a musical note. It's not a permanently stable object, but a specific energy at which the 4 neutrons can briefly sing together in harmony before flying apart. The quality of the data was significantly higher than the 2001 experiment, and it sent a new shockwave through the theoretical physics community. Here was a much stronger piece of evidence that this impossible particle might be real. So what would it mean if the tetraneutron is confirmed? The implications are nothing less than revolutionary. Our current understanding of the strong nuclear force is encapsulated in a powerful framework called chiral effective field theory. This theory has been spectacularly successful at explaining the interactions between protons and neutrons in all the nuclei we know. But this entire framework is built on the foundational principle that forces between nucleons, protons, and neutrons are predominantly pairwise. This means the force acts between 2 particles at a time. The binding of a nucleus is essentially the sum of all these individual 2-body interactions. The existence of a stable tetraneutron would shatter this assumption. It would provide undeniable proof that there are fundamental multi-neutron forces at play, that 4 neutrons can interact with each other in a way that is more than just the sum of their pairwise interactions. It would be like discovering that a group of 4 people can lift a weight that is far heavier than what any 2 pairs could lift separately, implying a mysterious collective form of strength that only emerges when all 4 work together. This would force a complete rewrite of nuclear physics textbooks and demand a new theoretical framework to describe these exotic multi-body forces. The hunt is far from over. The scientific principle of reproducibility demands that other labs around the world must see this signal in their own detectors before the tetraneutron can be accepted into the canon of known particles. New experiments are being planned at facilities like the Facility for Rare Isotope Beams in the United States, which will have the capability to create even more neutron-rich beams and probe these fleeting states with unprecedented precision. The quest to confirm or deny the tetraneutron's existence is a beautiful example of science at its most cutting edge, where a single, fragile data point can challenge the foundations of our knowledge and push us toward a deeper, more complete understanding of the forces that sculpt reality itself. Whether it is finally proven to be a new state of matter or an elaborate illusion, the tetraneutron has already achieved something remarkable. It has shown us that even the most established rules of physics are still open for debate. Yet as we explore the rules that govern the smallest particles, we must also consider the very recipe of the cosmos itself, a recipe written in the first moments of the universe that seems to have gotten one crucial ingredient terribly wrong. This is the cosmic lithium problem, a discrepancy so fundamental that it strikes right at the heart of our understanding of the Big Bang. In its earliest, hottest minutes, the universe was a primordial nuclear furnace, a state known as Big Bang nucleosynthesis. During this brief, explosive period, protons and neutrons fused to form the first atomic nuclei, primarily hydrogen, the fuel for all future stars, along with a significant amount of helium and a minuscule trace of lithium. For decades, cosmologists have used the incredibly precise laws of nuclear physics to calculate exactly how much of each element should have been created in this cosmic forge. Their predictions for the amounts of hydrogen and helium match the abundances we observe in the oldest stars nearly perfectly, a spectacular triumph for the Big Bang theory. But when it comes to that third element, lithium, the numbers break down completely. The universe contains only about 1/3 of the lithium-7 that our most sophisticated models insist should be there. It's as if a master baker followed a perfect recipe for a cake, only to discover that one of the main ingredients had mysteriously vanished from the finished product. To grasp why this is so troubling, you have to appreciate the elegance and precision of the calculations. The physics of Big Bang nucleosynthesis is not guesswork. It is a tightly constrained set of equations that depend on well-measured quantities like the density of ordinary matter and the neutron lifetime. We can be so confident in the predicted helium abundance because it acts as a cosmic barometer. Its value precisely tells us the density of matter in the early universe, a value that later measurements of the cosmic microwave background have confirmed with stunning accuracy. The recipe is sound, so the severe shortage of lithium implies that something is missing from our equations. Either our understanding of the nuclear reactions that took place in the first 3 minutes is incomplete, or some process we haven't yet discovered has been actively destroying lithium for billions of years. Scientists have pursued two main paths to solve this puzzle, each with profound implications. The first path questions the initial conditions. Could unknown particles from the early universe have altered the nuclear reactions? Some theories suggest that if exotic particles, like certain types of dark matter, were present during nucleosynthesis, they could have changed the reaction rates, effectively reducing the yield of lithium-7. Others have explored whether our measurements of the key nuclear cross-sections, the probabilities that certain fusion reactions will occur, might have small, overlooked errors that collectively add up to this significant discrepancy. However, after decades of refinement in both theory and experiment, no adjustment has successfully resolved the mismatch without throwing the perfect predictions for hydrogen and helium into disarray. This has led many researchers down the second path, the idea that the lithium was created correctly in the Big Bang but was then destroyed later. The evidence for this comes from the astronomers' perfect time capsules, ancient metal-poor stars known as population Roman II stars. These stellar relics formed from nearly pristine gas not long after the Big Bang, and their atmospheres preserve a chemical record of the early universe. It is in these stars that we consistently measure the lithium abundance, and it is always about 3 times lower than predicted. The challenge is figuring out what inside these stars could have consumed the lithium. Normal stellar fusion isn't the answer. The cores of these stars are hot enough to burn hydrogen into helium, but not nearly hot enough to destroy lithium. In fact, their surfaces should be cool enough to preserve it. One compelling theory involves a process called diffusion, where heavier elements slowly sink down from a star's visible atmosphere into its hotter interior over billions of years. If this process is more efficient than we thought, it could have dragged lithium atoms down to depths where the temperature was just high enough to burn them. Another fascinating idea posits that these ancient stars might have been far more active in their youth than we assume. If they had strong, sun-like magnetic fields and powerful stellar winds in the past, the resulting spots and turbulence could have deepened the outer convective zone, again allowing lithium to be carried to hotter regions and destroyed. The problem is that these mechanisms would affect other light elements like beryllium and boron in ways we don't consistently observe, leaving the mystery only partially solved. The cosmic lithium problem endures as a quiet but persistent thorn in the side of modern cosmology. It's a reminder that for all the grand success of the Big Bang Theory, there are still minute details in the universe's first recipe that we have yet to decipher. This tiny discrepancy in the amount of a single element points to either a gap in our knowledge of nuclear physics or a missing chapter in the life story of the oldest stars. It proves that sometimes the biggest secrets of the cosmos are hidden not in the vast emptiness between galaxies, but in the faint spectral lines of a humble element, waiting in the atmosphere of an ancient star for us to finally read its story. But just when we think we have the universe catalogued into neat categories of particles and forces, a theoretical wildcard emerges from the equations, a concept so bizarre it seems to tear up the rulebook of reality itself. This is the idea of the unparticle, a proposed substance that doesn't just add a new particle to the menu, it challenges our very definition of what a particle is supposed to be. Our entire understanding of the physical world is built on the concept of particles, tiny, discrete packets of energy and momentum that have a specific mass and obey well-defined rules. An electron has a certain mass, a photon has none, but they are both particles in the sense that they are quantized and measurable. The unparticle theory, first proposed by physicist Howard Georgi, dares to ask, what if there's an entire hidden sector of reality that doesn't play by these rules at all? What if there exists something that behaves like a particle in some ways, but lacks its most fundamental property? This radical idea stems from the pursuit of unity in physics, the grand aim to describe all forces and particles under one elegant theoretical framework. Many such theories, including various versions of string theory, predict that our familiar universe is just one part of a larger reality, and that there could be other sectors operating alongside ours, governed by their own unique rules. Often, these theories involve very high energy particles that are far too massive for our current colliders to detect. But Georgi explored a fascinating possibility. What if a hidden sector isn't made of heavy particles, but is instead described by a principle known as scale invariance? In simple terms, a scale invariant system has no fixed reference for size or energy. It looks the same at all scales. Think of a fractal coastline. Whether you view it from space or from a few feet above, its pattern of irregularities looks similar. It has no characteristic length. Now, apply that idea to a fundamental substance. An unparticle field would have no fixed mass scale. It wouldn't be made of individual, countable particles with a specific weight. Instead, it would manifest as a continuous, ethereal stuff that doesn't fit into our standard boxes. So what would this stuff actually do? How could we possibly detect something that, by its nature, evades our standard classifications? The theory suggests that this hidden sector could interact with our own familiar matter, but only very weakly, through what's known as a higher dimensional operator. In practice, this means that if unparticles exist, they could reveal themselves in high-energy particle collisions by stealing away energy and momentum in a very distinctive non-particle way. Imagine watching a perfect game of billiards where the balls always conserve energy and momentum in a predictable fashion after a collision. Now imagine one collision where the cue ball hits another, and instead of the target ball rolling away with a specific speed, the energy seems to vanish into a weird, foggy substance that doesn't have a single energy but a continuous spectrum of possibilities. That's the kind of signature physicists would look for: a smeared-out, continuous distribution of missing energy that doesn't match the sharp, discrete signature of a known particle like a neutrino. This is where the story connects to real-world mystery. The initial allure of the unparticle concept was its potential to explain certain anomalies seen in high-energy experiments. There were hints in the data from particle colliders and even in studies of the behavior of neutrons that didn't quite fit the standard model. The unparticle provided a tantalizing, exotic explanation for these slight deviations. It proposed a hidden world that could leave its fingerprint not just in colliders, but also in the way stars cool or in the precise forces between particles. However, as is often the case in science, more data has largely closed the window on those specific anomalies. Subsequent, more precise experiments have failed to confirm the initial odd results, and the constraints on such a hidden sector have become incredibly tight. The simple, elegant versions of the unparticle model that Georgi first proposed are now heavily disfavored by the data, yet the idea is far from dead. It has evolved. The core conceptual breakthrough that there could be scale-invariant sectors with fractional scaling dimensions has fertilized other fields of physics. The mathematics of unparticles has found surprising applications in condensed matter physics, helping to describe strange phases of matter in certain materials that exhibit similar scale-invariant properties. Furthermore, while the original motivation may have faded, the philosophical challenge it presents endures. The unparticle remains a powerful reminder of how limited our intuition might be. For centuries, we've forced nature into a particle or wave dichotomy. The unparticle screams that there might be other possibilities, forms of matter and energy so alien that we lack the language to describe them properly. It stands as a testament to theoretical physics at its most creative, daring to imagine a world beyond particles, a hidden layer of reality operating by a set of rules we are only just beginning to conceive. But perhaps the most profound challenge to our understanding of reality isn't found in a distant void or a fleeting particle, but in the ultimate cosmic shredder, a black hole. For decades after their prediction by Einstein's theory of general relativity, black holes were thought to be the universe's ultimate vaults. Whatever fell in a star, a planet, an entire library of information, was gone forever, crushed into a single point of infinite density at the singularity, and sealed behind an event horizon from which not even light could escape. They were the end of the story, a one-way street to oblivion. That all changed in the 1970s when a young Stephen Hawking performed a brilliant calculation that merged general relativity with quantum mechanics, only to uncover a paradox so deep it has haunted theoretical physics for half a century. He discovered that black holes aren't truly black. Hawking realized that the intense gravitational field just outside the event horizon should spontaneously create pairs of virtual particles as quantum fields fluctuate everywhere in space. Normally, these particle-antiparticle pairs pop into existence and annihilate each other almost instantly. But at the edge of a black hole, a strange theft can occur. One particle of the pair might fall across the event horizon while the other escapes into space. The escaped particle carries away energy, and to conserve energy, the black hole itself must lose mass. This gradual leakage of radiation, now known as Hawking radiation, means that black holes slowly evaporate. Given enough time, a black hole will radiate away all of its mass and vanish completely. This was a stunning revelation, but it came with a catastrophic implication. The Hawking radiation is purely thermal. It's random noise whose properties depend only on the black hole's mass, charge, and spin. It contains no information whatsoever about the specific things that fell in. So when the black hole finally evaporates, what happens to all that information? The detailed quantum states of every atom, every particle, every book that ever crossed the horizon seem to have been erased from the universe. This creates the black hole information paradox, and it's a direct assault on a cornerstone of quantum mechanics, unitarity. This principle states that information cannot be created or destroyed, it can only be transformed. The entire evolution of the universe, from the Big Bang to the present, should be reversible in theory. If you could track every single quantum state, you should be able to rewind the tape. Hawking's calculations suggested that black holes violate this most sacred law. They appear to take the rich, complex information of everything they consume and turn it into featureless thermal radiation, a process that is fundamentally irreversible. For years, Hawking himself argued that information was indeed lost forever, a claim that led to a famous bet with fellow physicist John Preskill, who insisted that information must somehow be preserved. The struggle to resolve this paradox has pushed theoretical physics to its absolute limits, giving rise to some of the most mind-bending ideas in modern science. One of the most prominent solutions is the holographic principle, which suggests that all the information that falls into a black hole is not lost inside it, but is instead encoded on its two-dimensional event horizon, much like a hologram where a three-dimensional image is stored on a flat surface. When the black hole evaporates, this information is somehow imprinted onto the Hawking radiation that escapes, ensuring it is not lost. This principle radically reimagines our universe, proposing that reality itself might be a projection from a two-dimensional surface at its boundary. An even more drastic solution is the firewall hypothesis. This idea proposes that to preserve information, the event horizon cannot be the smooth, uneventful space that general relativity predicts. Instead, it must be a seething wall of incredibly high energy particles, a literal firewall that would instantly incinerate anything trying to cross it. This would prevent information from ever falling into the black hole in the first place, solving the paradox but utterly violating Einstein's principle of equivalence, which states that free fall should feel like floating in empty space. The existence of a firewall would mean that the event horizon is a place of violent drama, not a silent point of no return. Other theories suggest that black holes don't evaporate completely but leave behind a tiny, information-packed remnant, a plank-sized fossil containing all the data of what fell in. However, this introduces its own problems, as such an object would have to be capable of storing an almost infinite amount of information in a vanishingly small space. The debate remains fierce and unresolved. Recent advances in string theory and the study of quantum entanglement have provided new mathematical tools to probe the problem, with some calculations suggesting that information can escape through complex correlations within the Hawking radiation. But a full, universally accepted solution remains the holy grail of theoretical physics. The information paradox is more than an arcane puzzle. It is a crucial battleground where our two most powerful theories of reality, general relativity and quantum mechanics, clash in a fundamental way. Unraveling it may not only tell us what happens to what falls into a black hole, but could also provide the key to a deeper, unified theory of quantum gravity, revealing the true nature of spacetime itself. Yet as we ponder the information swallowed by black holes, we can also consider a different kind of emptiness much closer to home, a stark and unexpected boundary at the very edge of our own solar system. Far beyond the orbit of Neptune, in the cold, dark realm where the sun is just a particularly bright star, lies a vast expanse of icy debris known as the Kuiper Belt. This is the solar system's attic, a swirling disk of frozen leftovers from the planetary formation process over 4 billion years ago, home to dwarf planets like Pluto and Eris. For decades, our models predicted that this population of objects should continue, albeit thinning out gradually for a significant distance. But then our telescopes got better, and we started to map this distant frontier in detail, only to discover that the solar system appears to have a very abrupt and unexpected edge, a boundary so sharp it has been named the Kuiper Cliff. Around 50 astronomical units from the Sun, 1 being the distance from Earth to the Sun, the number of Kuiper belt objects doesn't just slowly decline, it plummets. It's a drop-off so dramatic and sudden that it's as if someone built a celestial wall out there, a sharp boundary to the construction site of our planetary system. This is profoundly puzzling because our standard model of solar system formation doesn't predict such a clean edge. The primordial disk of dust and gas from which the planets formed is thought to have extended much farther out, and the gentle dynamical processes that shape the Kuiper belt should have left a more extended, tapering population of objects. The existence of this cliff suggests that something dramatic happened in the solar system's past, an event that swept this region clean or shepherded the objects into a very specific and confined zone. This strange absence has fueled one of the most compelling and controversial theories in modern planetary science: the existence of a large, undiscovered planet lurking in the extreme outer darkness. This hypothetical world is often referred to as Planet 9. The idea is that a planet several times the mass of Earth but on a highly elongated and distant orbit could be gravitationally shaping this outer edge. As it travels on its multi-thousand-year loop around the Sun, its immense gravity could be shepherding the Kuiper belt objects, either hurling them inward toward the Sun, ejecting them from the solar system entirely, or trapping them in orbital resonances that prevent them from existing beyond a certain distance. In this scenario, the Kuiper cliff isn't a natural end to the disk of material. It's the signature of an invisible shepherd, a massive perturber whose gravitational influence defines the boundary of our familiar solar system. The hunt for this planet is ongoing, with astronomers meticulously scanning the sky for the faint, slow-moving dot that would confirm its existence. However, Planet 9 is not the only possible explanation for this celestial drop-off. Another fascinating possibility harks back to the solar system's violent and dynamic youth. The early planetary system was a chaotic billiard table, with giant planets migrating from their original formation positions. It's possible that during this period of instability, our ice giant planet, a world similar to Uranus or Neptune, was gravitationally ejected from the solar system entirely by a close encounter with Jupiter or Saturn. As this doomed planet was flung outwards on its escape trajectory, its gravity would have acted like a plow, scattering and clearing out a huge swath of the primordial Kuiper belt in the process, leaving behind the sharp cliff we see today. This ancient planetary encounter could have sculpted the edge, a ghostly fingerprint of a lost sibling planet that now wanders alone in the interstellar void. There are, of course, less dramatic potential explanations. It could be that our observations are simply incomplete. Detecting these incredibly faint, distant objects is enormously challenging, and it's possible that there is a population of dark, low-albedo objects beyond the cliff that we haven't yet been able to see. Alternatively, the answer might lie in the finer details of how the primordial solar nebula collapsed and dissipated. Perhaps the disk of material truly did have a much sharper outer edge than we currently model, though this would itself require an explanation. The Kuiper cliff stands as a stark reminder that even our own cosmic backyard still holds major surprises. It challenges the notion that we have a complete picture of our planetary family and suggests that the history of our solar system may have been far more dynamic and eventful than we ever imagined, potentially with a massive, unknown world still waiting to be found or the ghost of a lost one hinting at a dramatic past. Yet, even as we detect these unimaginably energetic particles from the void, a fundamental cosmic rule suggests that most of them should never have reached us at all. This rule is known as the Greisen-Zatsepin-Kuzmin cutoff, or simply the GZK cutoff, and it acts as a universal speed limit for protons traveling across the vastness of intergalactic space. The universe may be mostly empty, but it is far from a perfect vacuum. It is filled with the faint, cold afterglow of the Big Bang itself, the cosmic microwave background radiation. This is a bath of low-energy photons that permeates every cubic inch of the cosmos, a relic from a time when the universe was a hot, dense soup. Now imagine an ultra-high-energy proton, a single subatomic bullet fired from a cosmic accelerator billions of light-years away, racing toward Earth at nearly the speed of light. On its immense journey, it is virtually guaranteed to collide with one of these background photons. And according to the laws of physics, when a super-fast proton smashes into even a low-energy photon, something very specific happens. The interaction is so powerful that it allows for the creation of new particles, specifically a pion. This process saps a significant amount of energy from the original proton. The GZK cutoff, predicted in 1966, calculates the maximum energy a proton can have after traveling for more than about 150 million light-years and still undergoing these constant, draining collisions. It's a fundamental energy ceiling, a point beyond which protons from distant sources should be slowed down to a level below that threshold. They simply cannot arrive at our doorstep with energies that break this limit. This is why the detection of cosmic rays that appear to have shattered the GZK ceiling is so deeply perplexing. It creates a fascinating and frustrating paradox. The particles we detect with these ultra-high energies are so powerful that only the most extreme events in the universe, things like active galactic nuclei or colliding galaxy clusters, could possibly have created them. But according to the GZK limit, such particles cannot have traveled from very far away. Therefore, the sources of these ultra-high-energy cosmic rays must be relatively close to us, cosmically speaking, within our local supercluster of galaxies. They have to be in our backyard, and this is the heart of the mystery. When we point our most powerful telescopes at the regions of the sky from which these particles seem to originate, we find no obvious, monstrously powerful engine capable of such a feat. Our corner of the universe is relatively quiet. We should be surrounded by the faint echoes of these incredible particle accelerators, but we see only silence and darkness. It's as if we are finding cannonballs in our backyard, but there is no cannon in sight. Scientists have proposed several candidates for these hidden cosmic accelerators, but each one presents its own set of challenges. The primary suspect remains active galactic nuclei, the intensely luminous cores of galaxies where supermassive black holes are actively devouring matter. The chaotic environment and powerful magnetic fields surrounding these black holes are perhaps the only places capable of accelerating particles to such breathtaking energies. The problem is that the nearest known active galactic nuclei are still quite far away, and their exact position is difficult to pin down because the cosmic rays themselves are charged particles. Their paths are not straight lines, they are curved and twisted by the magnetic fields that fill the space between galaxies, making it incredibly difficult to trace them back to a single point of origin. It's like trying to find the source of a river by following a single drop of water that has been blown about by a chaotic wind. Other theories point to less common but even more violent events, such as the shock waves from the merger of entire galaxy clusters cataclysms that release more energy than anything else in the modern universe. Some have even speculated about the decay of hypothetical super-heavy dark matter particles left over from the Big Bang, which would decay and release their immense energy as particles that could then travel to us unimpeded from relatively short distances. The ongoing hunt for the sources of these super-energetic particles is led by enormous observatories like the Pierre Auger Observatory in Argentina, a detector array that covers an area of over 1,000 square miles. These facilities don't detect the cosmic rays directly. Instead, they observe the enormous showers of secondary particles they create when they slam into the upper atmosphere. By studying the direction and nature of these cascading showers, physicists painstakingly piece together the energy and potential origin of the primary particle. The results have been tantalizing but inconclusive. There have been statistical hints of correlations between the arrival directions of the highest energy events and the locations of nearby active galaxies or other energetic objects, but no single definitive source has been identified. The particles are also incredibly rare, arriving at a rate of about 1 per square kilometer per century, which means collecting enough data is a slow and patient process. The GZK cutoff mystery forces us to confront the possibility that some of the most powerful and violent engines in our galactic neighborhood are still operating in plain sight, yet remain completely invisible to our conventional telescopes, known to us only by the microscopic, universe-spanning shrapnel they fire across the void. Yet even as we map the vast flows of galaxies and the subtle echoes of the Big Bang, a more fundamental crisis is brewing in the very numbers we use to define the cosmos, a discrepancy so persistent and significant that it threatens to crack the foundation of modern cosmology itself. This is the Hubble tension, and at its heart is a single, deceptively simple number, the Hubble constant. This value, denoted as h0, is the current rate of the universe's expansion. It tells us how fast, in kilometers per second, a galaxy 1 megaparsec away is receding from us. Pinpointing this number is arguably the most important quest in all of cosmology, because it not only describes how the universe is behaving today, but also allows us to retrace its entire history back to the Big Bang. For decades, astronomers have pursued two primary, independent paths to measure this crucial number, confident that their methods, though different, would ultimately converge on a single, universal truth. Instead, they have diverged, creating a chasm between our understanding of the universe's infancy and its present state that is growing wider and more undeniable with each passing year. The first path looks back to the beginning, to the cosmic microwave background. The Planck satellite, which mapped this ancient afterglow with exquisite precision, provides a snapshot of the infant universe at 380,000 years old. The tiny fluctuations in temperature and density revealed in this map are a cosmic blueprint. By applying our extremely well-tested model of the universe, the lambda cold dark matter model, to this blueprint, we can run the cosmic film forward to predict what the Hubble constant should be today. This is a top-down, model-dependent approach. The answer it gives is incredibly precise, approximately 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. This value is derived from the physics of the very early universe and assumes our standard model is complete and correct. The second path measures the universe directly around us, building a cosmic distance ladder rung by rung. This is a bottom-up, empirical approach that doesn't rely on a model of the early universe. Astronomers start with parallax measurements to nearby stars to calibrate the distance to Cepheid variables, pulsating stars whose intrinsic brightness is directly tied to their pulsation period. By finding these Cepheids in nearby galaxies, they can calibrate the true brightness of Type Ia supernova, those brilliant standard candles that can be seen across billions of light years. By measuring how much the light from these supernovae is redshifted and comparing it to their precisely known distances, astronomers can directly measure the Hubble constant in the modern universe. The team led by Nobel laureate Adam Rees, using the Hubble Space Telescope to perform this painstaking work, has arrived at a starkly different value, roughly 73.0 kilometers per second per megaparsec. The difference between 67.4 and 73.0 might seem small, but the uncertainties of each measurement are now so incredibly tiny that the gap between them is over 4.5 sigma, meaning there is only about a 1 in a million chance that this discrepancy is a fluke. It is a real conflict. This isn't a case of one measurement being right and the other wrong. Both methods have been refined and cross-checked to an extraordinary degree. The Planck data is a masterpiece of precision cosmology, and the distance ladder team has meticulously eliminated potential sources of error, even using the James Webb Space Telescope to confirm their Cepheid measurements by looking through the dust of distant galaxies. The tension is robust. This leaves us with a thrilling and unsettling possibility. The discrepancy is not an error but a clue. It may be the first hard evidence that our standard cosmological model, the lambda-CDM model that has been so spectacularly successful for decades, is incomplete. We may be missing a piece of physics. Theorists have rushed to propose what that new physics could be, and the ideas are as profound as they are diverse. Some suggest that the properties of dark energy are not constant, as represented by Einstein's cosmological constant, but are dynamic. Perhaps this mysterious force is growing stronger over time, which would accelerate the expansion faster than predicted. Others point a finger at dark matter, speculating that it might have some unusual interaction with itself or with dark energy that we haven't accounted for. Another compelling idea involves early dark energy, an exotic form of energy that may have briefly surged in the very first moments after the Big Bang, altering the universe's initial conditions just enough to throw off the Planck prediction while leaving the local measurement untouched. There are even more radical suggestions, like the existence of a new type of relativistic particle that flooded the early universe, or that our local region of the cosmos is part of a vast underdensity, a Hubble bubble that is expanding faster than the average, though this latter idea is heavily constrained by other observations. The Hubble tension is more than just a technical disagreement over a number. It is a potential portal to a deeper understanding of reality. It forces us to ask whether the laws of physics as we know them have remained constant across 14 billion years, or if something fundamental has shifted. It is a mystery that pits the ancient universe against the modern one, and right now they are telling us two different stories. Resolving this tension is one of the most urgent goals in all of science, because the answer won't just give us a number. It will likely reveal an entirely new chapter in the story of the cosmos. Yet the allure of a constructed cosmos doesn't end with a single star's strange dimming. The idea of alien megastructures has evolved from a wild speculation into a serious framework that scientists are now actively using to interpret other cosmic anomalies. This brings us back full circle, not to a specific observation, but to a profound shift in perspective, the search for technosignatures. Unlike the traditional SETI search for radio signals, which listens for a civilization's conversations, the hunt for megastructures looks for evidence of their industry, for projects of such immense scale that they become visible across the interstellar gulf. The most famous theoretical construct is the Dyson sphere, proposed by physicist Freeman Dyson in the 1960s. The concept is one of ultimate energy harnessing, a civilization so advanced that it requires the total energy output of its home star, and so builds a vast swarm of orbiting collectors to capture that energy. This swarm would partially enclose the star, and in doing so, would radically change its appearance to outside observers. Instead of emitting most of its energy in the visible light spectrum, the star's light would be absorbed by the collectors and re-radiated as waste heat in the infrared. To our telescopes, such a star would appear as a bizarre combination. A sun that is strangely dim in visible light but brilliantly bright in the infrared, a signature that is entirely unnatural. This is not just science fiction, it is a hypothesis that has been operationalized. Astronomers have already sifted through data from infrared telescopes like NASA's WISE mission, scanning millions of stars for exactly this unusual combination of optical dimness and infrared brilliance. While no definitive candidate has been found, the very act of looking legitimizes the idea. It moves the question from "are we alone?" to "what would the footprint of a galaxy-spanning civilization actually look like?" The possibilities extend far beyond a full Dyson sphere. A civilization might build giant orbital rings, vast solar panel arrays, or even planet-sized supercomputers known as matryoshka brains, which use a star's energy for information processing. Each of these could produce its own unique and potentially detectable astrophysical signature. The lingering mystery of Tabby's star, even with its likely dust-based explanation, proved the value of this approach. It demonstrated that our data is now precise enough to identify objects that behave in highly unusual ways, forcing us to consider all possibilities, no matter how extraordinary. This new era of technosignature hunting is being led by ambitious projects like Breakthrough Listen, the most comprehensive scientific search for intelligent life beyond Earth ever undertaken. With thousands of hours dedicated on some of the world's most powerful radio telescopes, like the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, its primary goal is to listen for artificial signals. But its scope is far broader. It also uses optical telescopes to search for powerful laser pulses that could be used for interstellar communication, and it analyzes vast archives of astronomical data for other potential technosignatures, including the kind of light curves that might be produced by giant orbiting structures. The project treats the sky as a haystack of natural phenomena, meticulously searching for the one needle that doesn't belong, a needle that might be a beacon, a broadcast, or the shadow of an incomprehensibly large construction project. The profound question, then, is what the confirmation of such a discovery would actually mean for humanity. Finding a single, unambiguous technosignature, be it a radio transmission or the light curve of a megastructure, would instantly answer the ancient question of whether we are alone. But the implications would run far deeper than that. The mere existence of such a structure would tell us that the apparent laws of physics are not just theoretical possibilities, but can be practically engineered on a stellar scale. It would prove that intelligence is not a fleeting, self-destructive phase, but a force that can persist for timescales long enough to reshape entire star systems. The technological gap between us and such a civilization would be so vast that their capabilities would be indistinguishable from what we might call magic. They would likely be millions of years more advanced, and their motivations, their culture, and even their physical form would be utterly beyond our comprehension. This is the ultimate weight of the megastructure theory. It is not merely a potential solution to an astrophysical puzzle. It is a window into a possible future for intelligence itself, a future of cosmic-scale engineering and immortality. And simultaneously, it is a mirror held up to humanity, reflecting both our profound loneliness and our audacious hope. The continued, serious scientific search for these artifacts is a testament to that hope, a belief that the universe might not only be strange and beautiful, but that it might also, somewhere, be inhabited by beings who looked up at their own night sky and decided to build something magnificent enough to be seen from the stars. And so our journey through the cosmos's greatest puzzles comes to a close, a tour that has spanned from the immeasurably vast to the vanishingly small. We have witnessed the ghostly gravitational pull of dark matter, an invisible hand shaping the destiny of galaxies, and felt the repulsive push of dark energy, a mysterious force tearing the very fabric of space-time apart at an ever-increasing rate. We've stood at the edge of a black hole, grappling with a paradox that threatens to unravel our understanding of information itself, and we've marveled at the quantum weirdness of a potential tetraneutron, a particle that by all rights should not be able to exist. We have traced the silent, immense river of galaxies flowing towards the unseen Great Attractor and puzzled over the perfect, haunting geometry of the Red Rectangle Nebula, a masterpiece carved by a dying star. What unites these 25 phenomena from the galactic to the subatomic is not that they represent failures of science, but rather its greatest triumphs. Each one is a beacon, illuminating the very edge of our understanding and challenging us to push further. They are the unanswered questions that prevent cosmology from becoming a closed book, the mysteries that ensure the next generation of telescopes, experiments, and brilliant young minds will have profound work to do. This relentless collective pursuit of the unknown is the engine of discovery, a reminder that science is not a static set of facts but a dynamic, evolving conversation with the universe. It is in these gaps in our knowledge, these tantalizing cracks in reality, that the next revolution in physics is most likely to be hiding. This sense of shared wonder is what connects us all. Every one of us has looked up at a starry night sky and felt that primal curiosity, that desire to understand our place in the grand scheme of things. These mysteries belong to everyone, so now we want to hear from you. Which of these cosmic enigmas captured your imagination the most? Does the eerie silence of the Fermi Paradox make you ponder our solitude, or does the fleeting blip of the wow signal fill you with hope? Are you drawn to the immense scale of the Boötes void or the quantum-scale defiance of the tetraneutron? Let us know in the comments below. We read every single one. If this exploration into the unknown left you wanting more, you're in the right place. Our channel is dedicated to deep dives into the universe's most fascinating secrets, from the edges of black holes to the search for alien life. Make sure to subscribe and hit the bell so you don't miss our next journey into the cosmos. The universe is vast, strange, and full of stories yet to be told. We can't wait to continue exploring them.